So we're on to chapter 10. Chapter 10 is another statistics concept. We learned one statistics concept that was chapter 9, that was confidence intervals, which is a really big topic and really important. What we're going to do now, chapter 10, hypothesis test, is another big stats concept. It's more complicated. That's the bad news. The good news is we're going to do so many hypothesis tests that you're going to have no choice but to get good at it. Because everything in chapter 10, 11, 12, and 13, they're all hypothesis tests. We're going to be doing hypothesis tests almost for the remainder of the semester, except for like the last day of class, we're going to have some different topic. Other than that, all hypothesis tests. So, and then when you take the final, you'll be good on hypothesis tests because we will have done so many of them and it'll be fresh in your mind because we just finished them. All right, so because hypothesis tests is a more difficult concept, I made up a story to tell you. I'm going to tell you a story. It's a cartoon story that I made up to try to make it a little bit easier to understand hypothesis tests. Okay, so bear with me here. Focus really hard. If you guys have any questions on anything, any little detail of the story, please let me know. But today what we're going to do is we're going to do section 10.3. Of all the sections in chapter 10, I think 10.3 is the easiest one, so I start with that one. So we're going to do kind of 10.1 and 10.3 together. 10.1 is kind of like hypothesis test stuff that applies to all hypothesis tests. And then section 10.3 is one specific type of hypothesis test where it's a hypothesis test for a mean. Okay, so anyway, we're going to work on this one specific type, but as I tell you the story, I'll be explaining, stuff in 10.1. But anyway, 10.3 is what we're doing today. So here's the story. So everybody get focused and get ready. And here's how the story goes. So we have this big bag of numbers. Okay. You need to imagine this is population data. Okay, remember every stats problem is about a big group. And if you collected data from the big group, you can answer the question and you don't need stats. But we don't collect data from the big group. So how do we answer the question about the big group if we haven't collected data from the entire big group? That's all of stats. So this bag here, I want you to imagine we collected data from the entire big group, okay? And all the answers are in this bag. For example, if I want to know the average age of all Rio Hondo students, let's say, you're supposed to talk to all Rio Hondo students and ask them for their age. If I was to ask every single Rio Hondo student for their age, I put all their answers in this bag over here. So this bag would be filled with ages of Rio Hondo students. Since there's 20,000 Rio Hondo students, there'd be 20,000 numbers in here. But in reality, we don't collect this data. So this is an imaginary bag of data. So we're starting off with an imaginary bag of data. We don't have all the data to do any calculations with. Okay, so we start off with a big bag of numbers. And today in section 10.3, what we want to know is the average of all the numbers in the bag. We're dying to know the average of all the numbers in the bag. And we use the symbol mu for that. Remember, there's two symbols for average. Mu is the one we use if it's the average of all the numbers in the big bag. Okay, so we're dying to know what mu is. And we're freaking out. Oh my God, I need to know mu right now. I gotta know, freaking out. And then the king comes along. So we got the king. The king says, guys, relax. I know what mu is. I'll tell you what it is. I know the average of all the numbers in the bag, so you don't have to, relax. And he says, the average of all the numbers is 20. That's what he's saying. Okay, so we start off with a big bag of numbers, but we don't have all these numbers in front of us. We're dying to know the average. King says, don't worry. The average of all the numbers is 20. Now the king, everybody loves the king. He's an honest king. He's never lied to you before, and you always pretty much believe him. Anytime he says something, you believe him. So you're like, okay, the king said it's 20. The average of all the numbers is 20, and you can relax. You're happy now. You're like, okay, now I know what the average is. But even though most people are happy because they all believe the king, there's one person who does not believe the king. I call him the peasant. The peasant says, no, guys, don't listen to the king. He's wrong this time. I know you love him, whatever, but he's wrong this time. The peasant comes and says, the average of all the numbers is less than 20. So there's an argument going on over here. King says the average of all the numbers in the entire bag is 20. Peasant says the average of all the numbers in the entire bag is less than 20. Okay, we want to just tell the peasant, shut up, get out of here. We believe the king. Who are you? Go away. But the peasant won't shut up. The peasant's like, guys, you need to listen to me. The king is wrong. The average of all the numbers is less than 20. We're like, okay, fine. We have to decide who to believe now. And if we could calculate the average of all the numbers in the bag, if we could actually calculate mu, then we'd know who's right. If we calculate mu and we get 20, then the king is right. If we get a number less than 20, then the peasant's right. But we can't calculate mu because we don't have all this data to calculate it from. So what do? What we do is it's always the first step in every stats problem. What you do is you take a sample, meaning you're going to take some numbers out of this bag, and you're going to calculate the average of the numbers in your sample, which is called XBar. Remember, mu and XBar are both averages. What's the difference? Mu is the average of all the numbers in the bag. XBar is the average of just a sample of numbers from the bag, some of the numbers in the bag, not all of them. So in order to decide who to believe, we're going to take a sample and calculate XBar. And we're going to look at this answer. And based on this answer, we're going to decide, does that answer make us believe the king, or does it point to the peasant? Think of this as us gathering evidence. Okay, so we're gathering evidence, and based off the evidence, we decide, does the evidence point to the king being right, or does the evidence point to the peasant being right? Okay, so that's how we decide who to believe. Remember, they're not arguing over XBar. They're arguing over mu, the average of all the numbers. But we don't have all the numbers, so we take a sample, those are like numbers we have, and we calculate XBar, and based on that answer, we'll decide who to believe. So that's what it says over here. So to settle the dispute, to decide who to believe, you're going to take a sample, only one. You're going to give the peasant one shot. We're going to take one sample, we're going to calculate XBar, and based off this answer, we'll decide, should we believe the king, or should we say, no, the king's wrong this time, we need to believe the peasant. Okay. Now, don't forget that XBar is our best one number guess for mu. So XBar is supposed to be close to mu. So if the king is right when he says mu is 20, that doesn't mean XBar has to be 20, but XBar should be close to 20 is what that means. Now, if you're not sure who to believe, you're going to side with the king. Because again, he gets every benefit of the doubt. We love him. He's an honest king. But so the only time we're going to believe the peasant is if there's overwhelming evidence in favor of the peasant. Otherwise, we believe the king. Okay, so now we take a sample, we calculate XBar. If you get an XBar that's exactly 20, who do you think we should believe?
The king?
Yeah, we're going to believe the king. Yeah, because I'm basically wondering, is this number close to 20? Well, if it's exactly 20, it's definitely close to 20. So we believe the king. So if you take a sample, calculate XBar, and you get 20, we're going to side with the king. Okay, if you get an XBar bigger than 20, okay, this time I don't even care if it's close to 20 or not, because the peasant is saying less than, and we're getting greater than. I know it's different letters, but peasant saying less than 20, we're getting something bigger than 20 for XBar. That's not enough evidence. That's not evidence at all in favor of the peasant. So automatically in that situation, we side with the king. Okay, if you calculate XBar and you get less than 20, a lot of times I'll ask the students, but I'm not going to ask you guys. If I ask, okay, who do you believe? A lot of people will just say the peasant, but that's wrong. This is the most important situation, the interesting situation. If XBar is less than 20, who do you believe? The answer is it depends, because just because you see a less than, don't automatically side with the peasant. Because again, if mu is 20, that's the average of all the numbers. If you take a sample, could the average be less than 20? Sure. If you take a sample, it's just the average is supposed to be close to 20 if the king is right, but it could be less, or it could be bigger, or it could be equal. So if it's less, who do you believe? It depends. What does it depend on? It depends on how close to 20 it is. Okay. If XBar is less than 20, but close to 20, because it's close, we still believe the king. So think about it like this. An XBar less than 20 is a little bit of evidence in favor of the peasant, but the fact that it's close to 20 is some evidence in favor of the king. That's not overwhelming evidence in favor of the peasant, so we believe the king. Remember, we love the king, he's an honest king, so we just have a small bit of evidence in favor of the peasant, but we have some evidence in favor of the king. We're giving it to the king. The only time we're going to believe the peasant is in this last situation here. If XBar is less than 20, but it's also far from 20, okay? It has to be less than. That's like a little bit of evidence in favor of the peasant because he's saying less than. But again, if the king is right that mu is 20, XBar is supposed to be close to 20. So if it's far from 20, it's like that's more evidence in favor of the peasant. Then in that situation, we believe the peasants. Okay, that's the story of hypothesis tests. I'm going to probably tell you the whole story one more time because it's super important. And every hypothesis test has a story very similar to this one. So every day from now till we're done with chapter 13, I'm going to start off the lecture with a story like this. It'll be a little bit different every time, but today they're fighting over averages, depends on what letter they're fighting over. Before I go over the story one more time, does anyone have any questions so far? Okay, so just because it's so important, I know you could watch the video later and listen to the story 100 times, but it's so important. Let's just go through it one more time. Okay, so we're starting off with a bag of numbers, but we don't have all these numbers to calculate things from. It's an imaginary bag of numbers, and the average of all of them is what we care about today. In section 10.3, we care about the average of all the numbers, and we're dying to know what it is. We don't know what it is. But the king comes along and says, guys, I know what it is. The average of all the numbers in the bag is 20. Guys, relax. I know it's 20. And everybody's happy because the king he's truthful king. He's never lied to you before. He's an honest king. Everyone loves the king. You're like, yes, use 20. Great. Everyone's happy. Not everyone, almost everybody. But then the peasant comes along and says, no, the king is wrong. The average of all the numbers is less than 20. Okay. Now, we want to believe the king, but the peasant is insisting that the king is wrong. The average of all the numbers is less than 20. So to decide who to believe, so we have to decide who to believe. If we could calculate mu, remember mu is the average of all the numbers. If we could calculate it, we'd know right away. If mu is 20, king's right. If it's less than 20, peasant's right. But we can't calculate it. We don't even have this data to calculate it from. So what do? Again, you do what you always do in a stats class. You take a sample. It's like you put your hand in the bag and take some numbers out, and you calculate the average of the numbers in your sample, which is X bar. Because that's the best you can do. You take as many numbers as you can out and calculate the average of those. And based off this answer, you'll decide who to believe. So the way we decide who to believe is we take a sample and calculate X bar. Remember, they're not fighting over X bar. They're fighting over mu. Mu is the average of all the numbers. That's what they're fighting over. X bar is the average of a sample of numbers, some numbers. That's the data we actually have. And the idea is that X bar is supposed to be close to mu because X bar is our best one number guess for mu. So if the king is right that mu is 20, X bar should be at least close to 20. But again, it doesn't mean it has to be equal to 20. X bar, if the average of all the numbers in the bag is 20, if you take a sample, the average of the numbers in the sample, X bar, could be less than 20, could equal 20, or it could be more, as long as it's supposed to be close. That's all I know. I just don't know which side it's on. Okay, so again, this is us gathering evidence. We're collecting evidence to decide who to believe. We take a sample, calculate X bar, and that's our evidence. And does our evidence point to the king being right, or does it point to the peasant being right? So it depends on what X bar we get. If you get an X bar that's exactly 20, again, I'm expecting it to be close to 20 if the king is right. Well, if it's exactly 20, it's definitely close to 20, so we believe the king. If X bar is greater than 20, I don't even care if it's close anymore because the peasant is saying less than. If the peasant says a less than and we get a greater than for X bar, that's not evidence at all in favor of the peasant, so we automatically believe the king in that situation. Obviously, you believe the king. But then the most interesting one, the one that will happen pretty much every time we do a problem, is this situation. If X bar is less than 20. So we're getting something that's less than 20 for X bar. Peasant saying less than, so we see a less than and a less than. Who do you believe? Don't automatically side with the peasant just because you get a less than. Because again, if the king says mu is 20, X bar could be less than 20. As long as it's close, the king could still be right. And we want to give the king every benefit of the doubt. So who do you believe when X bar is less than 20? The answer is it depends. If X bar is less than 20, but close to 20, because it's close to 20, we're still going to believe the king. Okay, so that's not overwhelming evidence in favor of the peasant. If we don't have overwhelming evidence in favor of the peasant, we're going to believe the king. But if X bar is less than 20 and far from 20, again, the less than 20 is like a little bit of evidence in favor of the peasant. Far from 20 is more evidence in favor of the peasant, because again, if the king is right, it should be close to 20. So that's like a lot of evidence in favor of the peasant. So that's the situation where we believe the peasant. All right, that's the story of hypothesis tests. I mean, I got to tell you a lot more, but that's the basic story. Any questions? All right, sounds good. Okay, a couple extra things to add in here. So one thing I want to add in here is the king's claim will always have an equal sign in it. Okay, so just always has an equal sign. The peasant can claim three separate things. What he's claiming depends on the problem. You have to read the problem carefully to see what the peasant is claiming. Here I have him claiming less than. So he could say less than. That would be one situation. If it's not less than, he could claim a greater than, or he could claim a not equal to. So there's three options for what the peasant can claim. King's claim will always have an equal sign, and the peasant's claim will either be a less than, a greater than, or a not equal to. How do you know? You read the problem carefully, and then you'll be able to figure that out. That's the first thing I want to tell you. The next thing I want to tell you is, think of this as a court case. If somebody is on trial in a court, they're innocent till proven guilty beyond a reasonable doubt. They tell you, you have to be beyond a reasonable doubt. In other words, if somebody's in court on trial for something, and they produce evidence, and it's just a little bit of evidence that the person's guilty, but it's not overwhelming evidence, then they say the person's not guilty. It's called innocent till proven guilty. So there has to be an overwhelming evidence in favor of, overwhelming evidence that the person is guilty. Otherwise, they say the person's not guilty. So same thing. Think of it as like the king is on trial. Okay, so we think the king is lying. We're going to put him on trial, but we need overwhelming evidence that the king is lying. Otherwise, we're going to say, no, we're going to believe the king. Okay, so it's really analogous to like a court case kind of thing. All right. So the next thing I got to explain to you is, how do we know if we're close to 20 or far from 20 over here, right? If X bar is close to 20, you believe the king. If it's far from 20, believe the peasant. How do we know, like if our X bar is 19, is that close to 20? If it's 17, is that close to 20? What if it's 12? Is it close to 20? How do we know if it's close or if it's far? That's the next thing. So we're trying to figure out how close is the X bar answer and the king's claim of mu. How close are they? So are X bar and mu close or far from each other? That's kind of the next question. How do we figure out if they're close or far? Okay, so let's go on to the next slide. How can you tell if two numbers are close together or far apart? Okay, so let's say I give you the number 10 and the number 14. Would you say these numbers are close together or far apart? Don't answer, because everyone's going to say their own thing. Someone's going to say they're far apart, someone's going to say they're close together. It's a vague question what I asked you. You can't really answer it. Are they close together or far apart? But in a stats class, you can answer if they're close together or far apart. It depends on the standard deviation. So are these close or far? Okay, so it depends on the standard deviation. What am I talking about? I'm talking about that original bag of numbers in the last slide, the standard deviation of all the numbers in the bag, sigma. Standard deviation kind of measures an average spread, like a typical spread. If you take two numbers out, it's a typical spread. It gives you an idea of what close and far is basically what it does. So let's say the standard deviation of all the numbers in the bag is 2, okay? I want you to now think of the standard deviation as a step size. So imagine there's a number line, okay? And here's the number 10. And this is, like you're standing on the number line, and you're going to walk to the number 14. If you take one step to the right, you end up at the number 12. So every time you take one step, you've moved over this much. I'm going to write like we added a standard deviation. So you just move one step to the right, you're at the number 12. So think of standard deviation as like your step size. Like every time you take a step, you've moved 2 feet or something like that. If you take one more step, you're at the number 14. It's like I added one more standard deviation, and now we're here. How many steps did it take us to go from the number 10 to the number 14? It took us 2 steps. Okay, but the number of steps will depend on what your standard deviation is. So if the standard deviation of all the numbers in the bag is 2, then 10 and 14 are 2 steps apart. And does that mean close together or far apart? Okay, you just tell me, if you walk 2 steps, do you feel like you walked a lot or you didn't walk a lot? Is that
Didn't walk a lot.
Yeah, it's not that much walking. It's 2 steps, not that much. So they're close together is what it means. The number 10 and the number 14 are close together. Now, I'm going to give you a rule of thumb that we're going to use just for the next couple of slides, and then you're going to forget it because we're going to get a better rule when we do problems. But just for the next couple of slides, let's use the number 3 as a cutoff. If I walk more than 3 steps, I'm tired. Okay, less than 3 steps, I'm not tired. I'm joking, but you get the idea. So we're going to use the number 3 as a cutoff. So if the numbers are more than 3 steps apart, we're going to say they're far apart. If they're less than 3 steps apart, they're close together, just for the next couple of slides. Then we're going to throw out this rule. So because 2 steps is less than 3 steps, they're close together. Now, what if the standard deviation of the numbers in the bag, instead of it being 2, was 0.5? Okay. Then if you start walking along your number line, let's say we start at the number 10. That's you. And you take 1 step, that means you moved over 0.5. You're now at the number 10.5. You take another step, so it's like I add the standard deviation every time. We're now at the number 11. So every time you take 1 step, you've moved like half a foot, something like that. Okay, so every single step gets you add basically 0.5 every time. So let's say I took 3 steps there. Let's keep going. Where am I trying to get to? I'm trying to get to the number 14. Take 1 more step. We're at the number 12. Take another step. We're at 12.5. Another step, we're at the number 13. Another step, 13.5. And 1 more step, we're at the number 14. Okay, so think of the standard deviation as a step size. Every time you take a step, you moved over 0.5. If you start at the number 10, how many steps does it take to get to the number 14? How many steps?
A lot of steps.
How many though? How many exactly?
8.
8, yeah. So the numbers are 8 steps apart. So when the numbers are 8 steps apart, are they close together or far apart?
Further apart than the other one.
Right. Well, we're just going to say they're far apart in general. Far apart. If this is more than 3, far apart. If the numbers are less than 3 steps apart, they're close together. So in a stats class, that's how we tell if numbers are close together or far apart. It depends on the standard deviation of the numbers in the bag. Okay. Now, so are the numbers 10 and 14 close together or far apart? Okay, so we already answered this, but again, it depends on the standard deviation. If sigma is 2, they're 2 steps apart, so they're close together. If sigma is 0.5, they're 8 steps apart, so they're far apart. So it depends on the standard deviation of all the numbers in the bag, because standard deviation gives you a step size, gives you like a typical distance between 2 numbers. So if the 2 numbers are a lot of steps apart, if you have to walk a long ways to get from one number to the other one, then they're far apart. If you don't have to walk that far, close together. Again, just for the next couple of slides, we're going to use the number 3 as the cutoff. If the numbers are more than 3 steps apart, they're far apart. If they're less than 3 steps apart, close together. But again, after just a couple more slides, we're going to forget that rule. We'll get a better rule later. Okay, now you saw how I drew pictures to figure out how far apart the numbers are. You're not going to want to draw pictures like that, especially if they're 8 steps apart. You're not going to want to draw that plus sigma 8 times kind of thing. And there's going to be some problems where the numbers are not a nice number of steps apart. It might not be 2 steps or 5 steps or 7 steps. It might not be a whole number. It might be an ugly number, like the numbers are 5.386 steps apart. How are you going to figure that out? So we need a better way to figure out how far apart the 2 numbers are instead of drawing a picture kind of thing. All right, and the way we're going to figure that out is with the Z transformation formula. So you've seen the Z transformation formula before. And I mentioned to you before that there's a lot of different uses of this formula. We used it to calculate probabilities in chapter 7. There's another application in chapter 2 that we didn't talk about. We skipped that, but we're going to use it again here. Basically, whenever you calculate a Z number, it's like you're calculating how far apart, how many steps apart 2 things are. This formula will tell you how far apart the top 2 things are. Whatever the top 2 things are that are being subtracted, you want to know how far apart they are, plug into the formula, and your Z answer will be how many steps apart the numbers are. Here, check it out. Okay, so basically what I'm writing here is I'm doing the same question as before. We have the numbers 10 and the number 14. I want to know how far apart they are if the standard deviation is 0.5. We already did this. The answer was they're 8 steps apart. But I want to show you how we do this by plugging into the formula. So I'm going to plug into the formula. Now the question becomes, what do you plug in here and what do you plug in here? It doesn't really matter, but I just wrote it. I wrote mu is 14 so that you plug in the 14 here, and x is 10 so you plug it in here. Okay, so don't worry so much about all the words and all this stuff over here. But let me just go ahead and plug in. You plug in the 10 here, and then minus 14 here, and then divide by standard deviation with 0.5. When you calculate this on the calculator, you do the top first. 10 minus 14 is -7. Then you divide by 0.5, you get -8. We'll talk about the negative in a minute, but the 8 is telling me they're 8 steps apart. So it's a much better way of figuring it out than drawing a picture kind of thing, because it would take a long time. Okay, so it tells me they're 8 steps apart. And I'm like, oh, okay, they're far apart. Now the negative is a little bit important, not too important, but let me explain a little bit. The reason why we're getting a negative is because this first number is less than the second number. So when you subtract, you get a negative. It's because the first number on the number line is on the left of the second number. So if you were going to read this result to someone, you could say it like this. The number 10 is 8 steps to the left. You read the negative sign as like to the left of the number 14. So 10 is on the left of 14. That's what this is saying. And they're 8 steps apart. 8 steps apart, and 10 is on the left of 14. That's what that's saying. Okay, so that kind of answers that one. All right, any questions on this much? All right, sounds good. Here's another one. We didn't do this one yet. But again, I'm basically asking you, how many steps apart are these numbers, 29 and 33, if the standard deviation is 0.7? How many steps apart are they? That's what I'm asking. So once again, this Z transformation formula will tell you how many steps apart the numbers are. Okay, here, let me write down the formula. So for X, we're going to put 33, and for mu, 29. And the bottom number is 0.7. And when you calculate this, let me get my calculator out. All right, so let's see. Well, the answer I'm getting for this is some real ugly number. I'm getting 5.714285.714, something like that. So anyway, but again, how would you figure that out? By drawing a picture? You wouldn't. It's a really nasty number, but the Z transformation formula calculates it really fast. So you tell me, are these numbers close together or far apart? So we're getting that the numbers are 5.7 steps apart. And remember, 3 is our cutoff. More than 3 far apart, less than 3 close together. So are they close together or far apart?
They're far apart.
Yeah, they're far apart because they're more than 3 steps apart. Okay, so that's the answer to part A. How many steps apart are they? They're 5.714, whatever steps apart, and they're far apart. And what does the sign of the answer mean? This time the answer is positive. So sometimes you get a positive answer, sometimes you get a negative answer. And again, the only reason we're getting a positive is because this first number is bigger than the second. So when we subtract on top, we get a positive. So if you were going to read this to someone, you would say the number 33 is 5.7 whatever steps to the right. Read the plus sign is to the right of the number 29 on the number line. It makes sense. 33 is on the right of 29. Okay, any questions so far? Okay, so now we've answered the question, how do we know if numbers are close together or far apart in a stats class? It all depends on the standard deviation of the numbers in the bag. Okay, now there's 3 types of hypothesis tests. Why is there 3 types? Because the peasant can claim one of 3 things, right? He has 3 options for what he can claim. The king only has 1 option. He's going to have an equal sign in his claim, and that's it. So here's one type of hypothesis test. Looks like this. H0 is basically the king's claim. They call this the null hypothesis. Null means 0. So H0 is the king's claim, and he's claiming mu is equal to 20. H1 is the peasant's claim. Some other books, instead of H1, they call it HA. They might put a capital A or a lowercase a. HA for alternate hypothesis. So we have H0, null hypothesis, and alternate hypothesis. The null hypothesis is the king's claim. The alternate hypothesis is the peasant's claim. Anyway, H0 and H1. And in this case, the peasant is saying mu is less than 20. So it's just like what we saw on the first slide. Okay, so this is one type, okay? Where basically this type is where the peasant says less than, okay? Because again, the king will always say equals. This is exactly the claims on the first slide that we looked at today. Now I'm going to remind you, I'm going to go through the first slide again, but I mean, I'm not going to take you to the first slide, but I'm going to remind you of the story. How do we decide who to believe? We take a sample, right? Every time you want to decide who to believe, you take a sample. And what are we going to calculate? We're going to calculate XBar. Based on our XBar answer, we're going to decide, should we believe the king or should we believe the peasant? Okay, since we're going to calculate XBar, we need to look at the XBar distribution. We looked at the XBar distribution in section 8.1. Remember, XBar is a variable because it depends on your sample. So, and then we also know in section 8.1 that under certain conditions, XBar will have a normal distribution. So we're going to look at the XBar distribution. Looks like that. Basically, when you take a sample and calculate XBar, your answer will land somewhere on this number line. Okay, so when you take your sample and calculate XBar, it will land on the number line somewhere. All right, guys, help me out here, okay? If you take a sample and calculate XBar, and you get exactly 20, I'm basically just saying the first slide stuff again. If you get exactly 20, who do you believe? If your XBar is 20, who do you believe?
The king.
You believe the king, that's right. Okay. If your XBar is greater than 20, like over here, or over here, or over here, or anywhere greater than 20, who do you believe?
The king?
You believe the king, that's right. Because the peasant is saying less than, and we're getting greater than. So if you get a greater than, that's not evidence in favor of the peasant at all, so you automatically believe the king. Okay, what if you get an XBar less than 20 like this, but close to 20? That's pretty close to 20. Who do you believe? So if you get an XBar less than 20, yes. If you get an XBar less than 20 but close to 20, you believe the king. If this is less than 20, still if that's close to 20, we're still going to believe the king. But there's going to be some cutoff line, okay, that if our XBar lands past the cutoff line, if our XBar is over here, then not only are we less than 20, but we're far from 20, then who do we believe?
The peasant.
Believe the peasant. So basically, believe the peasant anywhere in here. The peasant gets that part, and the king gets all this. Okay, so if the XBar answer lands anywhere in the green section of the number line, we're going to believe the king. If your XBar answer lands anywhere in the red section, we're going to believe the peasant. Notice how much the king gets and how little the peasant gets. And again, the reason is we're giving the king every benefit of the doubt. So it has to be super strong evidence in favor of the peasant to believe the peasant. That means our XBar answer has to be less than 20, so on this side of 20, and far from 20, that's when we believe the peasant. Okay, so what I want you, okay, so then this cutoff line here, this region over here, above the red section of the number line, the area there, this area here is called the rejection region. Rejection region basically means if your XBar lands in there, you reject what the king is claiming. You don't believe the king anymore. That's called the rejection region. So basically what I want you to get out of this little discussion here is that when the peasant says less than, the rejection region will be on the left side in your picture. That's what I want you to get. Okay, so there's the picture, rejection region, areas alpha. Once again, if your XBar lands anywhere here, you believe the king. But there's going to be a cutoff line, and if your XBar lands past the cutoff line, XBar lands anywhere there, you're going to believe the peasant. That's called the rejection region, and the area is going to be called alpha. So alpha stands for the area of the rejection region. Okay. So again, keep that in mind. When the peasant is saying less than, rejection region is on the left. Now, when we do problems, there's two ways to do it. One, we could use the XBar distribution, like it says over here, but we're not going to use the XBar distribution. Instead, we're going to use the T distribution. If we use the T distribution, it saves us maybe one or two little calculations. So that's the way we're going to do it. Why am I using T distribution? Because the king and peasant are fighting over mu. In chapter 9, same thing. When we built confidence intervals for mu, you had to use the T distribution. So same thing here. When we're doing a hypothesis test for mu, we're going to be using the T distribution. But other than that, everything else is pretty much the same. Instead of the mean being 20 here, the number here is going to be 0 because it's always a 0 in the middle there. Rejection region still on the left. The area of it is still alpha. Okay. And this type of test is called a left tail test. Left-tailed because the rejection region is in the left tail. Okay, that's one type of hypothesis test. That's if the peasant says less than. Another type is if the peasant says greater than. So again, the king is always going to say equal, but what if the peasant says greater than? Okay, so same idea. How are we going to decide who to believe? We're going to take a sample, calculate X bar, and based on our X bar answer, we'll decide who to believe. So we have to look at the X bar distribution. So here's the X bar distribution. And when you take a sample and calculate X bar, your X bar answer will land on the number line here somewhere. Okay. So again, I'm going to kind of take you through the first slide again, but this time the peasant is saying greater than, so watch out for that. So how do we decide who to believe? Take a sample, calculate X bar. If X bar is exactly 20, who do you believe?
The king.
You believe the king. What if X bar is just a little bit less than 20? Who do you believe?
The king.
You believe the king. What if X bar is less than 20 but really far from 20? Who do you believe?
The king.
Yes, good. Okay, I tried to trick you. You didn't let me trick you. Good. You believe the king because the peasant is saying greater than. Okay, so if you get a less than, if X bar is less than, I don't care how far it is, you believe the king. So the king gets all this. Okay, what if X bar is here? A little bit bigger than 20, but close to 20. Who do you believe? So it's greater than 20, but it's close to 20. Who do you believe?
The king.
You believe the king. But if X bar lands way over here, now it's bigger than 20 and really far from 20, then who do you believe?
The peasant.
You believe the peasant. So again, there's going to be some cutoff line. Okay. And if your X bar lands closer than that to 20, or on the left of 20, I don't care how far, you're going to believe the king. So the king gets that much. But if your X bar is past that cutoff line, meaning bigger than 20, so it has to be bigger than 20, like the peasant says, and really far from 20, if your X bar lands anywhere here, then we believe the peasants. So again, one thing I want to make sure you guys understand from this slide is when the peasant says greater than, rejection region is on the right. Okay, so you believe the peasant on the right side of the picture, basically. And again, the area of that region is called alpha. So rejection region is on the right, area is alpha. Alpha always stands for the total area of the rejection region. And again, when we do problems, we're not going to be using the X bar distribution. We're going to instead use the T distribution. The only thing that changes is the middle number is 0. Everything else is pretty much the same. Rejection region is still on the right side. The area of it is still alpha. And this is called a right-tailed test because the rejection region is in the right tail. So again, when the peasant says greater than, rejection region in the right tail. All right, the third type of test is if the peasant says not equal to. Okay, again, the king's claim will always have an equal to. What if the peasant says not equal to? Okay, once again, how do we decide who to believe? We take a sample, calculate X bar. But this time, the peasant is not saying which side of 20 he thinks mu is. He's just saying it's not 20. What that means is if X bar is 20 or close to 20 on either side, we're going to believe the king. But if it's too far from 20 on either side, we're going to believe the peasant. So there's going to be two cutoff lines in a problem like this. Okay, and if the X bar lands beyond the cutoff line on either side, we believe the peasant. Okay, so the peasant gets something on both sides because the peasant hasn't said which side he thinks it's on. The king gets the middle part, is basically the idea. All right, so when the peasant's claim is a not equal to, if the X bar is far from 20 on the right or far from 20 on the left, that's when you believe the peasant. Otherwise, if it's equal to 20 or close to 20 on either side, you believe the king. What that means is the rejection region has two pieces. There's a little piece of a rejection region on the left, little piece on the right. And alpha always stands for the total area of the rejection region, but in this situation, since the rejection region comes in two pieces, each piece gets an area of alpha over 2. Okay, so this area is alpha over 2, and this area is alpha over 2, so the total area is alpha. Okay, so remember that when the peasant says not equal to, the rejection region is on both sides. Okay, and each individual area is alpha over 2 because the total area is alpha. And once again, when we do problems, we will not be using the XBar distribution, we'll be using the T distribution. So, but everything else will be the same except for the fact that the middle number here will be 0. The rejection region, again, will be on both sides, and the total area is alpha. That means each individual area is alpha over 2. And this is called a two-tail test. So when the peasant says not equal to, it's a two-tail test. All right, and then here is a slide that has all of the tests on there. Everything we just talked about. Any questions so far? All right. So basically what I'm going to do now is I'm going to give you some formulas. And so the story is pretty much done. I just got to give you a formula or two, and then we can go ahead and do a problem. All right, quantity you're performing a hypothesis test about. What is the letter that the king and peasant are fighting over today? Someone tell me. What letter are they fighting over today?
Mu.
Mu. Today they're fighting over mu. And what, next lecture and following, they're going to fight over different letters. But today we're fighting over mu, which is the average of all the numbers in the original bag. Okay. Now, significance level. The significance level, alpha, area of the rejection region, they all mean the same thing. So the area of the rejection region, the symbol we use for it is alpha, and if it says, when they write it in words, they call it the significance level. So significance level, alpha, area of the rejection region, they all mean the same thing. Now, we're going to talk about problems, not today, next class, when an alpha is not given to you. What do you do when alpha is not given? But most of the time an alpha is given. And when an alpha is given, it's given so you can figure out where the cutoff lines are. So significance level is alpha. It helps you determine where the cutoff line for the rejection region is. Okay, probability distribution. Well, today we're going to use the T distribution, the T table. Okay, we're going to be using T table when we do problems today. Degrees of freedom. Remember, when you use the T table, you need a degrees of freedom formula. I'm sure you can guess what it is. It's n-1. We're going to see degrees of freedom a lot. The formula is going to be n-1 a lot. And then down the road, it may change to some other things. But for now, degrees of freedom is n-1. And that's just so we know what row of the table to use. And remember, n is your sample size. Test statistic formula. Okay. Remember earlier we talked about how to tell if two numbers are close together or far apart. And the way you do that is you use the Z transformation formula. What was it? X minus mu over sigma. That's the formula that lets me know how far apart the top two numbers are. I want to know how many steps apart they are, so I can know if they're close or far apart. Basically, I have to take this formula, though. This is not the right formula. I have to take this formula and adjust it to the situation we're in today. Every day, we're going to be in different situations. The situation we're in today, what are the two numbers that we're trying to see if they're close together or far apart? What are those two numbers? Well, there's the king's claim of what mu is, like he says mu is 20. And then how do we decide who to believe? We take a sample and we calculate X bar, and we want to see how close they are. So I want to know, is X bar and mu close together or far apart? That's the question. So the top shouldn't say X and mu, it should say X bar and mu. So I'm going to change the X to X bar. Basically, where the X is, the random variable we're using today is going to go there. So that's X bar. So now, and again, this formula will help me figure out how far apart those two things are. Now, if you put X bar down there, this should be sigma of X bar down here. Okay. So in chapter 8, we learned that sigma of x bar is equal to sigma x over square root of n. So I'm going to change the sigma of x bar down here to sigma x over square root of n. Or I could just write sigma over square root of n, where sigma is the standard deviation of all the numbers in the bag. So we're getting there. And now here's the deal. We don't know this. Just like in chapter 9, we don't know the standard deviation of all the numbers in the bag. How are we going to use this formula? The answer is we change it to S, which is the standard deviation of the numbers in your sample. Remember, the sample data you have, the population data you don't. So you change that to S. And then in chapter 9, we learned that if you change that to S, then we don't use the Z table anymore. We use the T table. All this formula is the Z transformation formula adjusted to the situation we're in today. Okay, so there it is. And it helps me figure out how many steps apart these are. The top two things that are being subtracted. I'm going to figure out how many steps apart they are so I can figure out if they're close together or far apart. That's the idea. All right, let's keep going. And then a condition. All right, remember, central limit theorem, chapter 8, applies to everything we do for the rest of the semester. It's in the background, at least, of everything we do for the rest of the semester. So we need central limit theorem to apply. That means I need x bar to have a normal distribution. And whenever I ask you to state central limit theorem, there's like two situations where x bar has a normal distribution, right? It's if n is greater than equal to 30, x bar has a normal distribution. Or if the original bag of numbers has a normal distribution, so does x bar. So the condition is populations from which samples are drawn have a normal distribution. That means the original bag on the very first slide today has a normal distribution, or our sample size is greater than equal to 30. Now, I'm not going to make you check this condition on quizzes or exams, but they may mention it in an online homework problem. Okay, so I want to make sure it's here so that I've told you a complete story, and so you have it in case you need it for the online homework. But again, all that condition is really saying is we need this so that central limit theorem applies, so that all the formulas work out the way everything works the way it's supposed to work, kind of thing. Okay, in some problems, n will be greater than 30, and you'll be like, great, x bar is normal, you won't have to worry about it. If the sample size is not greater than 30, the problem should say your population data, your original bag of numbers, has a normal distribution. If it doesn't say that, so some problems will say that. And if it does say that, be like, okay, great, and move on. You don't have to think about it too hard. And if it doesn't say that, we're just gonna assume it, okay? So somewhere in the section, it should say, in section 10.3, it should say, whether we mention it or not, it's always assumed that the original bag of numbers has a normal distribution if the sample size is not greater than 30. So again, I just want to say that to you so that you're prepared in case they talk about an online homework problem. Otherwise, don't worry about checking it. All right, I've now told you the complete story, and we're pretty much ready to do a problem. Does anyone have any questions? I know it's hard to have questions before we do a problem. Sometimes students will tell me, can you just stop talking and do a problem? You know, it's like almost like they shut their brain off until I start a problem, you know, but the story is so unbelievably important because this is actually the problem with math in general. I think one of the reasons people don't like math, there's a lot of reasons, I'm sure you guys can tell me some, but one of the reasons anyway is that, you know, you just don't know what you're doing. You just like, you see what the instructor is doing and you try to copy that, but you have no idea what you're actually doing. So the deal is your instructor should tell you the story. What are we trying to do? And then here's how I'm going to accomplish it, you know? So same thing over here. The hypothesis test is a big story, big concept we have to get down. Okay, and then we can do a problem. All right, let's go ahead and do a problem. Now, this is our first hypothesis test. It's going to take some time. So I know your brain should already be hurting from all the talking I've done so far. Let's take a couple seconds, try to clear your brain, then relax because this is going to be it's going to take some time to do this problem. So take a couple seconds and then we'll go ahead and start. Maybe I'm the one who needs the relaxing more than you, but I'm going to go ahead and relax for a couple more seconds. Okay. All right, let's go ahead and do this problem now. So, okay, what does it say here? According to the American Time Use Survey, the typical American spends 154.8 minutes per day watching television. Do internet users spend less time each day watching television? A survey of 50 internet users results in a mean time watching television per day of 128.7 minutes with a standard deviation of 46.5 minutes. Conduct the appropriate test to determine if internet users spend less time watching television at the 0.05 level of significance. Okay, so hypothesis problems are word problems, right? It's all words, okay? Okay, yeah, there's some numbers in there, mostly words. We have to pick apart this problem like crazy, and that's what we're gonna do. This problem is gonna take us a long time to get done, but I'm just gonna pick it apart. I'm gonna tear this problem to shreds, okay? We're gonna make sure we understand every little detail. Very first thing we need to understand, can you even tell that it's a hypothesis test problem? How do we notice that? Why do I care? Because on the final, listen, the next exam you're going to take, exam 4, all the problems are hypothesis tests, so you're not going to have a problem there. But on the final, it's cumulative. It's going to be a little bit of everything. And can you tell which problems are hypothesis test problems and which ones are not, kind of thing? It's a very common thing where someone will run a hypothesis test in a problem and it wasn't a hypothesis problem to begin with. So I want to make sure we can recognize it's a hypothesis test problem. Now, you may have had professors or teachers or whatever that have told you, when you're doing word problems, look for keywords. And I will tell you that is ridiculously wrong. They've misguided you. And if you know anyone who's told you that, give me their number so I can talk to them. Keywords can help sometimes, can hurt sometimes. Okay, so you don't want to just look for keywords. The right thing to do in a word problem is read it many times, understand the entire situation, and then you'll be good to go. Okay, but you really need to understand everything. Don't be like, I don't want to read all these words, just let me find the keyword and do it. It's a disaster. It could be a disaster. You might get lucky and it's not, but I'll show you. But when you're looking when you're trying to see if it's a hypothesis test, for that part, maybe keywords is okay. One thing is sometimes the problem will say, perform a hypothesis test. I mean, obviously, if it says perform a hypothesis test, okay, you know it's a hypothesis test problem. They don't say that. They do use the word test, conduct the appropriate tests. So that's a little bit of a hint that it's a hypothesis test. It says the word test. They say level of significance. That's a big one because level of significance only shows up when you're doing a hypothesis test. So that's good. And also when they give you an alpha, that's a little bit of a hint that it's a hypothesis test problem. But confidence intervals had alphas too. Just usually they don't give you the alpha in the problem for a confidence interval problem. They usually give you the confidence level and you have to calculate alpha. So if they give you an alpha, that's another little bit of a hint that it's a hypothesis test. So hopefully those little bits of advice make it obvious that it's a hypothesis test problem. So first thing, you recognize that it's a hypothesis test problem. Okay. After you've done that, every time you perform a hypothesis test, you're going to do the problem in 4 steps. It's always 4 steps. The first step is you're going to write down what the hypothesis test is. Meaning you're going to write down what the king and peasant are arguing over. You're going to write down H0. You're going to write down H1. And again, I'm going to take a long time on this because you really want to get this first part down and you want to get it right. If you get it wrong on an exam, okay, if you think it was a problem from a different section, you're probably going to get everything else, the whole problem wrong. You'll probably get a 0 on the problem. Yeah, I did give partial credit, but if you think it's one type of problem and it's a different type of problem, you're going to be using the wrong formula, wrong table, just everything's going to be wrong. So very important you get this part right. Let's make sure we know what the king and peasant are arguing over. So I guess the first thing is I want to know what letter they're arguing over. Clearly they're arguing over mu because that's all we've talked about, right? So I'm cheating. I'm saying it's mu because that's all we're talking about today, and this is our first hypothesis test. But I want to give you some advice. I'm going to give you a lot of advice as we talk through this problem. Okay, first bit of advice is sometimes average problems are hard to recognize. And so one thing you can do, which is a little bit of cheating, is try to rule out a percentage problem and try to rule out a standard deviation problem. I know we haven't talked about those yet, but once we've talked about those, you're going to have to decide, is it a percentage problem, a standard deviation problem, or an average problem? And I feel like those two are easier to recognize. So if you if you can rule out that it's a percentage problem, you can rule out that it's a standard deviation problem, then it's an average problem. Okay, that's one way to tell that it's an average problem. All right, but that's not a good way. I'm going to give you another way in a minute. But that's one thing to keep in mind. Now, let's talk about keywords. Let's look at the sentence over here. A survey, oops, sorry about that. A survey of 50 internet users results in a mean. They use the word mean. You go, oh, mean, average, mu. Great. If you see that word, you see that keyword, you're happy, you got it, mu. Okay. Mean time watching television per day of 120.7 minutes with a standard deviation. If you saw this word as a keyword, so to speak, you might think it's a standard deviation problem, which it's not. Okay. So you got to be really careful. Don't just look for keywords. Okay, it says mean there, and if you saw that word first, you got it right. If you saw this first, you thought it's a standard deviation problem, you got it wrong. And then down the road, it might be a standard deviation problem, and you might think it's a mean problem. So just don't look for keywords. So here's my next bit of advice, really good advice here. I'm giving you a lot of advice. When you're trying to figure out what H0 and H1 are, what I would do is, if there's a sentence in the problem that talks about the sample, don't look at it until after you figure out what the king and peasant are arguing over. This sentence is about the sample. Let's read it again. A survey of 50 internet users means they polled 50 internet users, right? And they asked each one of them, how much time did you spend watching television per day? And they calculated the average of those numbers to be 128.7, and standard deviation was 46.5 minutes. That sentence talks about the sample. What I would do if I were you is don't even look at that sentence until you figure out what H0 and H1 is. Because here's the deal. You don't take a sample and then decide what the argument is. First, the king and peasant are arguing, and then we take a sample to decide who to believe. Okay? So my advice is that if there's ever a sentence talking about the sample, I'm just going to erase it for now. I don't even want to look at it. Okay, so we're going to cross that out. We'll look at it later when we need it. But for right now, I'm just trying to figure out H0 and H1. Don't even look at that stuff. Now, if you look at the rest of the problem, they don't use the word mean or standard deviation or any of these keywords anywhere else. Okay, as I've already mentioned, average problems are the hardest ones to recognize sometimes. Some problems are worded very nicely and some of them are not. Okay, so this problem is not the best as far as the wording goes, so it's a little hard to tell, but here, this will be how we know. They say the typical American spends 154.8 minutes watching television. When you say the typical American, does that mean that every American spends 154.8 minutes watching television? No, that's an average. Okay, so when you say like so typical, that's sort of a key word if you want. Okay, if I say the typical Rio Hondo student is 23 years old, I don't mean that they're all 23. I mean on average they're 23. Okay, so again, it's problems are worded sometimes nicer than others. This one, they don't use the word average or mean anywhere, but it's an average problem because they say typical American, they're implying average there. Okay, so hopefully it's clear that the king and peasant are fighting over an average. So for H0, we're gonna have mu, and then you're gonna put equals, because the king's claim always has an equals. Okay, now we gotta figure out what number goes here. All right, that's another big part of the story. Here we go. Something that happens in this problem, it doesn't always happen, but the first 5 examples we do in this class, it's going to happen. But it doesn't always happen. So let me explain. In some problems, every stats problem is about a population, a big group, okay? But sometimes in problems, they'll mention 2 different populations, 2 big groups, but the question is only about one of them, okay? And so why do they talk about 2 groups if the question is about one group only? And the answer is because in the other group, we know the mean kind of thing, and we want to use that number for this group. Here, let me give you an example. I could do so we're going to leave this problem for a minute. Let's say I said, I think that the average age, I think the average age of all Rio Hondo students is 24.7 years old. Okay, and then the peasant can say whatever he wants to say, less than, greater than, not equal to, whatever it is. Okay. I can just say that, I think the average age of all Rio Hondo students is 24.7. Great. But someone might ask me, well, where'd you get this number from? Did you just make it up, or where'd it come from? So instead, what can happen is the problem can say the average age of all PCC students is 24.7. And what is the average, or let's write it like this, is the average age of all Rio Hondo students less than this? Okay, so I want you to take a look at that, the way it's worded here. There's two populations, all PCC students, all Rio Hondo students. Where's the question? The question is about Rio Hondo students, right? There's the question. So why do they mention PCC? There's no question about PCC. The average age of all PCC students is 24.7. Nobody is arguing over it. The argument is about Rio Hondo students. Okay, so why are they mentioning PCC at all? Just to try to explain to you where this number 24.7 came from, instead of just bringing it out of nowhere. Just, oh, boom, I think the average age of all Rio Hondo students is 24.7. So there's two populations. There's two mu's. There's a mu for all PCC students, and there's a mu for all Rio Hondo students. This one here is known. It's 24.7, and nobody is arguing over it. So they're telling you the problem. The mu for this population is 24.7. But our question is about the mu for another population, and I have no idea what it is. And the king is going to say, I think it's the same as it was for PCC students. So the king will say the mu for the Rio Hondo students is 24.7, and the peasant will say the mu for Rio Hondo students is less than 24.7. But again, the only reason to mention this other group is to explain to you where this number came from. It's kind of like so they can hand this number to you so you can use it in your tests. Okay? So instead of just pulling a number out of thin air, they're saying, well, for this one group, this is the number. For this other group, is it the same number or is it a different one, kind of thing? So now if I go back to this problem, let's go read it again from the top. In a typical, no, what does it say here? According to the American Time Use Survey, the typical American spends 154.8 minutes per day watching television. One population is all Americans, basically, and the average time they spend watching television per day is 154.8. That's a mu. That mu is known. Nobody is fighting over it. But then if you go to the next sentence, do internet users, that's a different group of people, right? There's some internet users that are not American. There are some Americans that are not internet users. It's a different group of people. Do internet users spend less time watching television? So there's two populations. One of the populations, I'll say the first population, is all Americans. And the average time for them, here, I'll just put AA, for all Americans, is 154.8 minutes. The second population is all internet users. And the mu for them, all internet users, let's say, we don't know what it is. So why do they, so okay, is the question about all Americans or about all internet users? Which one is this question about? Look at the problem. What's the question about? Is it about all Americans or is it about all internet users? Okay. Well, here's the question right here. Do internet users spend time watching television per day? The question is about all internet users. Okay. So the whole problem is about all internet users. That's the group the question's about. Because that's the group the question's about. Why do they mention all Americans? For one reason only, to hand you the number 154.8 to use in your tests. They're saying 154.8 is the average time all Americans spend watching television, but I want to know what's the average time all internet users spend watching television. And the king is going to say it's the same as it was for this other group. Okay, but this other group is not the group that the question's about. So the number 154.8 goes here. But let me say this one more time. I do not want you thinking of this as saying the average time all Americans spend watching television is 154.8. I know that's what it says. The average time all Americans spend watching television is 154.8. But that's not what this says. Because this mu is not about all Americans, it's about all internet users. Okay, so this sentence says the average time all internet users spend watching television is 154.8 minutes, meaning the king is saying for this group of all internet users, the average time is the same as for that other group. Okay, but again, this mu is all about internet users. All right, once you figure out that much, the bottom, H1, you're gonna put mu here, you're gonna put the same number here. We have to figure out what goes here. Is it a less than, a greater than, or a not equal to? Who could tell me?
Is it less?
Yeah, it's less than. It does say less over here. Do internet users spend less time watching television per day? It is a less. But again, you got to be careful to don't just look for keywords. Make sure you read the whole thing and understand it. Because we'll see a problem in here soon enough where it'll say less in the problem, but this will be a greater than instead of a less than. So you got to watch out for that. So it's not, don't just use keywords, but it is a less than over here. All right. After you figured out what H0 and H1 are, the last thing to do is to write down, if you use any symbols, we use the symbol mu, you got to write down what mu stands for in words. Mu equals what? All right. So mu is the average. Anytime you're writing down what mu stands for, you start by writing the average time. Now I'm going to write down the population, all internet users. Okay, so again, this question is about internet users. All internet users spend watching TV per day. All right, that is the first step of the 4 steps. Every time you do a hypothesis test, you're going to do it in 4 steps. First step, write down what the hypothesis is. Any questions on that one? All right, so then the second step is you're going to find the rejection region. We're going to draw a picture. And you're going to figure out where's the cutoff line where we stop believing the king and start believing the peasant kind of thing. When you're doing the rejection region, you're going to first write down alpha, which in this problem is 0.05. It's over here. And then you're going to write down the degrees of freedom if your problem has degrees of freedom. The only time you're not going to have degrees of freedom is if you're supposed to use the z table. But today we're using the t table. It needs degrees of freedom. The formula is n minus 1. N is our sample size. I'm going to have to erase this scribbled out part now so we could see what the sample size is. And it says a survey of 50 internet users. So 50 people is who we talked to, so n is 50. So the degrees of freedom is 49. Then you draw a picture. This is the t distribution. All right, important question here. What side is the rejection region on?
Left?
On the left side, that's right. The way you figure that out is you look at the peasant's claim, H1, and if it's a less than, the rejection region is on the left. So what you do is you put a tick mark on the left, you go up to the curve, and you shade to the left. Okay, so rejection region is on the left. We got to find this number here. Before we find it though, the area of the rejection region, the area I just shaded here, is alpha, 0.05. Okay, remember that's what alpha stands for, the area of the rejection region. Okay, so now we're going to look this up in the t-table, but there's a little bit of a problem. In order to look up a number in the t-table, you need to know the area in the right tail. The area you're looking up needs to be on this side in this tail, but this area is in the left tail here. So we're not going to be able to look it up. I mean, we are, but it's not going to be super easy. What you need to do, now this part that I'm going to draw, I don't want you to draw this, okay? Let me just draw it once so you can understand what I'm thinking. But you just do this in your head kind of thing. I want you to imagine flipping this area across this dotted line, like this dotted line here is a mirror. Okay, so draw the same kind of area, but in the right tail. This blue area here is like the mirror image of the red area. And this area here is 0.05. And I'm going to look up this number because if I know the area in the right tail, I can look up the number. So we'll start with that. But again, you just do that kind of in your mind. But don't draw it out. I'll leave it for a minute. But you don't want to draw it out because if you draw this on a quiz, I'm going to think you think it's a two-tail test. Okay, so I only want you to shade the left. But imagine, so this is the hardest one to look up in the t-table, okay? If you know the area in the left tail, what do? You kind of just flip it around, look up this number first, and then we'll go from there. So area in the right tail, 0.05, degrees of freedom, 49, and let's go to the t-table. Area in right tail, 0.05. See up here, it says area in right tail. It's got to be in the right tail to look it up. So area in the right tail, 0.05, degrees of freedom, 49. There's no 49. So use the closest one, which is 50. And then you go like this and like this. And the number is 1.676. Okay, so 49 wasn't there. When it's not there, use the closest one. So we used 50. Okay, and this number here is 1.676. But that's not the number I want. This is the number I want right here. Okay, so the last thing to do is to flip the number back around. You know, the numbers on the right side of 0 are positive. The numbers on the left side of 0 are negative. Okay, and so this number here is going to be negative. Well, what number is it? Okay, so all you do is take this answer, put it over there, put a negative in front of it. This is negative 1.676. All right, so that's it. So you look up that number. Now I'm going to erase all this because this was just, you just do that in your mind. Again, when you draw the picture on a quiz or an exam, do not draw the right side if it's a left tail test. This is what the picture should look like. But see, the number's negative. You'll never get a negative number out of the table. So if you look at the table, all the numbers in here are positive because it's expecting right tail area. So again, one more time, how do you look this number up? After you've shaded it, imagine the mirror image of this area on the other side, look up the number on this side, and then flip that number back over by putting a negative in front of it. So you have to put the negative in on your own because there's no negatives in the t-table. All right, so that's the second step, finding the rejection region. Any questions on that much? All right, let's go to the third step. The third step is the test statistic part. This is where you write down all the sample information and plug into the test statistic formula. The sample information, so the sample size was 50. They talked to 50 people, so we're looking at this sentence now. This is when you want to look at the sample sentence. Okay, if there's a sentence involving the sample, this is the time to look at it. So they talked to 50 people, 50 internet users. They asked each one of them, how long do you spend watching television per day? And they didn't give us those 50 numbers, the 50 data points, but they said they calculated the average. That was 128.7. That's the sample average, 28.7 minutes. And the sample standard deviation of those 50 answers was 46.5 minutes. So that's the sample information. So you write that down and then you plug into the test statistic formula. How do I know it's these things I need to write down? Because the test statistic formula is T equals X bar minus mu over S over square root of N. You're basically going to write down everything you need to plug into this formula. So I need to know X bar and S and N. Mu is the king's claim of mu. So you don't have to write that down, but you write down all the rest of the stuff and then plug into this formula. Okay, so let me go ahead and plug in. So X bar is 128.7. Mu, that's what the king is claiming mu is. Let's go back. He's saying 154.8 minutes. You look at H0, that's the King's claim, 154.8. Let's go forward. Okay, and then S is 46.7. No, 46.5 divided by square root of 50. Now you calculate this on the calculator. All right, now some advice. When you calculate this, calculate the top first and get the answer. Let me do that, 128.7 minus 154.8, answer. On my calculator, I'm getting negative 26.1 for that. Then you're gonna push divide for this fraction line here, so push divide. And now listen carefully because a lot of people get this wrong. When you're dividing by a fraction, my advice to you is before you type this fraction in, open some parentheses. So the open parentheses button is right above the number 8. I'm opening parentheses much times, and then 46.5 divided by square root of 50. And the answer I'm getting is negative 3.9689 21933. If you got that number, you typed it in right. If not, take my advice, open some parentheses before you type this. Whenever you're dividing by a fraction, the calculator will not do it the way you want unless you put the parentheses in there. Okay, that's the third step, test statistics step. Any questions on that step? Okay, the fourth step is the conclusion, but I don't know what to write yet. So what we're gonna do is we're gonna take this test statistic number and see where it lands on my rejection region picture. So I'm gonna take it back to the rejection region picture. Okay, so here comes that number. The number was, what was it? Negative 3.9689 21933. I want to know where on this number line is that number. That's where I want to know. And I want to know, is it in the rejection region or not? Because it's negative, it's on this side of 0. And because it's negative 3 point something, that's on the left of negative 1.67 whatever. So this number is on this side of the negative 1.676. So this test statistic number lands in the rejection region. If we land in the rejection region, that means we don't believe the king anymore. Okay. If the number would have landed here or here, then we would have said, okay, we should still believe the king. But if we land in the rejection region, the part where the shading is, then we don't believe the king anymore. That's the idea. All right, so we got to write the conclusion in words. Now, when you write the conclusion in words, well, it's two parts, but the first part, your options are reject H0 or do not reject H0. Those are the only two things you can write. You write anything else, it's going to be wrong. Please make sure you always, this first part of the conclusion is always about H0. Don't write something about H1. Don't write reject H1 or accept H1. Don't write the word accept. Don't write the word believe. There's only two options, reject H0 or do not reject H0. Same thing with the trial, right? In a trial, it's either guilty or not guilty. You don't say innocent. You say guilty or not guilty. Same thing here, reject H0 or do not reject H0. Which one is it going to be? If we land in the rejection region, you reject H0. If we don't, you do not reject H0. Let me go back again. This number landed in the rejection region, so we reject H0. It's like saying we reject the king's claim. So the first part of the conclusion is reject H0. So again, for that first part, these are your only choices. For every problem, those are your only choices. Reject H0, do not reject H0. That's it. If you land in the rejection region, you're going to write reject H0. If the test statistic does not land in the rejection region, you do not reject H0. Okay. And then the second part of the conclusion, you're going to write it in words. You're going to write the answer in words. What did we learn from this problem? What did we figure out? You're going to write it in words. When you write it in words, now it's all about H1. So this top part here is all about H0, reject H0, do not reject H0. But the part in words is all about H1. Let's go back. We're rejecting H0. That means we're not believing this. We're believing this. But you got to be careful how you write it in words. Do not ever write the word believe. I'm saying things so that you understand, but you got to write it a certain way. The wording is very important. So don't write believe H1. In the situation where you reject H0, you're going to say evidence suggests that we believe H1, but don't write the word believe. So you're going to start off by writing evidence suggests. Let's go back here. Evidence suggests. And instead of writing believe H1, I'm just going to write what H1 is. Evidence suggests this. So I'm going to write that down now. But I want to write it in words. So I don't want you to write the symbol mu. Instead of writing the symbol mu, write what mu is in words. Evidence suggests that the average time all internet users spend watching television per day is less than 154.8 minutes. So you're just going to write this down. Just write this in words, write this symbol in words. Okay, the average time, okay. So evidence suggests that, oops, I went the wrong way. Evidence suggests that the average time all internet users spend watching TV per day is less than 154.8 minutes. And that's how you do example 1. Any questions on example 1? Okay, so I'm going to just do another recap of example 1, and then we'll go on to another example. So, okay, this time I'm going to explain from the king and peasant standpoint. Don't ever write king and peasant, by the way, okay? King and peasant is my story to try to help you understand hypothesis better, okay? But I'll just real quickly from the king and peasant standpoint. Here's the idea. There's a big bag of numbers, okay? And the king is saying the average of all the numbers in the big bag is 154.8. The peasant is saying the average of all the numbers in the bag is less than 154.8. So we're trying to decide who to believe. How do we decide who to believe? We take a sample, calculate the average. And they said we took a sample of 50 people and the average was 128.7. 128.7 is less than 154.8. But does that mean we automatically believe the peasant? No. Our sample average, the 128.7, has to be less than 154.8 and far from 154.8 before I can decide who to believe. So I need to decide how far is 128.7 from 154.8. Are they close together or far apart? And that's what the test statistic formula does. When you calculate the test statistic, I'm trying to figure out how far apart is the 128.7 from the 154.8. The answer is negative 3.9, about negative 4 steps apart. Okay. Now, is 4 steps apart close together or far apart? Remember earlier today I said 3 is the rule of thumb? Well, we're throwing that out. 3 is not the rule of thumb. How do I know if 4 steps is close or far apart? The rejection region, this number is our cutoff number. So instead of the cutoff number being 3 or whatever it is, it's going to be a different number for every problem. In this problem, negative 1.676 is the cutoff number. If this is on the left of that, so it's more than, okay, I guess it's less than negative 1.6 steps apart. Negative 3.9 steps is more steps apart than negative 1.676. Oh, they're really far apart is what that says. So if your test statistic, this is just telling me how far apart these two numbers are. And if we land in the rejection region, they're too far apart to continue believing the king. So we side with the peasants. And then the only other thing is you got to make sure you write everything correctly. Don't ever write believe or accept or anything like that. And don't ever mention king or peasants. Yeah. All right, that's how example 1 goes. Last chance. Any questions on example 1? Okay, so here's the deal. When I write PowerPoints, when I write down my lecture notes, in every section I usually put 3 problems. There's one of them's a left tail test, one of them's a right tail test, one of them's a 2-tail test. I put one of each so you can see one of each. but I don't do them all in my lecture if I don't have time. Okay, so we're gonna do one more problem, but there's 2 more problems in the lecture notes. So I think we'll skip example 2. But I did do example 2 in my other stats class on Thursday. So if you want to see example 2 done, which you should go check it out, you can just go click on Math 132 on my website, click on Math 132, click on videos and watch the example 2 part of the lecture that I gave last time. But because if I try to do all 3, we'll definitely run out of time, I'll just do one more. So we're going to go ahead and skip example 2 for now. All right, guys, on to example 2. Okay, Michael Sullivan, the son of the author of your textbook, decided to enroll in a reading course that allegedly increases reading speed and comprehension. Prior to enrolling in class, Michael read 198 words per minute. The following data represents words per minute read for 10 different passages read after the course. Was the class effective? Use the 0.10 significance level. All right, so first thing, again, let's make sure we can see that this is a hypothesis test question. Again, if you are looking for some keywords, significance level is definitely, you only see that when it's a hypothesis test problem. And then when they give you an alpha, that's a hint, not a 100% confirmation, but a hint, again, that it's that a hypothesis test problem. So anyway, there's nothing really else that tells me that. So we'll just go with that. That's a hypothesis problem. But again, sometimes the problem says perform a hypothesis test or do a test, or they might use the word claim, test this person's claim or whatever. So some other kind of words that might be helpful to recognize that it's a hypothesis problem. It's definitely a hypothesis test problem. Okay, now when you do a hypothesis problem, like I said, you always do it in 4 steps. The first step is you're going to write down what the hypothesis test is. We're writing down what the argument is. What is the king saying? What is the peasant saying? Okay. And again, this is an average problem. And how do you tell it's an average problem? Again, one thing you could do is try to rule out percentage problem and try to rule out standard deviation problem. If you can rule those out, then it's an average problem. That's a little bit cheating, but that's some advice. Other than that, look what it says. Prior to the class, Michael read 198 words per minute. What does that mean he read 198 words per minute? Does that mean every single minute he reads exactly 198 words? No. It means on average he reads 198 words per minute. So a reading rate is an average. It's on average. If you read for a lot of minutes, he's reading on average 198 words per minute. So this is an average problem. So for the king's claim, we're going to write mu, and then we're going to put an equal sign because the king's claim always has an equal sign. Now we've got to figure out what number to put next to the mu. All right, so I think it's pretty clear it's the 198. That's the only number in the problem. But again, I want to make sure you guys understand there's 2 populations in this problem. There's a population, right, first population, and then there's a second population. Because it says prior to enrolling in the class, he read 180 words per minute. The first population is basically all passages. You don't have to write this down. That he read before he took the course. And the second population is all passages that he read after taking the course. The average time before the course is 198 words per minute. The average time after the course is what they're fighting about. Okay, so this is the question, what the question's about. The question's all about after the course, what happened to his reading rate, to the average time it takes him to read things, whatever. Okay, so the question's about this population. So why do they mention this population here? Why do they mention what happened before the course? Only for one reason, to give you the 198 number, to explain where the 198 came from. What's the average time it took him to read? What was his average reading rate before the course? 198. It's not being argued over. Everyone agrees it's 198. What's his average or his reading rate after he took the course? That's what we're arguing over. Okay. The king is going to say that it's the same as it was before the course. Like if he didn't get better, it's the same. So the king is going to say 198 here, but again, I don't want you to think of this as saying his reading rate before the course is 198. That's not what this says. What we're saying here is his reading rate after the course is still 198 like it was before. Okay, so that mu here is for after the course. I want to make sure everyone's clear. This whole question is about after the course. They only mention before the course so they can provide this number to you and explain kind of where it came from. Okay, so the king is saying his reading rate after the course is the same as it was before. It's 198 words per minute. The peasant is going to say, so we're going to put a mu here. We're going to put the same number here, 198 words per minute. We have to decide what symbol goes there. It's going to be a less than, a greater than, or a not equal to. The chat is saying something. Let's see. You're saying greater than. Yes, you're right. Because it says that it's supposed to increase, this course is supposed to increase a person's reading speed. And we're asking, was the class effective? Effective at what? At increasing the reading speed. If it did increase the reading speed, the average would be greater than 198 words per minute. Yeah, cool. All right. So that's H0, that's H1. And then you got to write down what mu stands for. Anytime you use a symbol here, you got to write down what it stands for in words. So let's go ahead and do that now. This is, there's a couple of ways to write it. You can, if you write reading rate already means average, so you don't have to put the word average. But you could, if you write average reading rate, technically that doesn't make sense, but I would like to see the word average. So it'd be nice if you wrote the word average. I'm going to write it slightly differently to get the word average in there. I would like to get the average word in there. I would like to get the word all in there. Okay, because it's an average for some population data or whatever that we don't have. So this is the average number of words per minute Michael reads for all passages read after the course. Now, again, you don't have to write something this extensive. You could just say Michael's reading rate after the course. You know, that's fine. But at least this way, it's more words, but it's got the word all in there. It's got the word average in there. All right. Any questions on that first part, the hypothesis part? Okay. The second step is you're going to write down, you're going to find the rejection region. This is a picture letting me know when do you believe the king, when do you believe the peasant. You have to write down alpha, which in this problem is 0.10. And you got to write down the degrees of freedom. In this problem, we have, so he read 10 passages, and here's the data for those 10 passages. So n is 10. So degrees of freedom is 9. And then you draw a picture. The rejection region is basically a picture. This is the t distribution that I'm drawing. So put a 0 there, label it t distribution. All right, next question. What side is the rejection region on? Left side, right side, or both sides? The chat is saying right side. You are correct. It's on the right side because the peasant's claim is a greater than. So anytime the peasant's claim is a greater than, rejection region's on the right side. So you're going to put a tick mark on the right. You're going to go up to the curve, and you're going to shade to the right. This area that I'm shading is alpha. It's the significance level. It's the area of the rejection region, which I wrote up there is 0.10. Okay, so this area here, 0.10. And now you got to look up this number over here. And that's the easiest one to look up in the t-table because t-table, you can look things up if you know the area in the right tail. This is the right tail right here. Area in the right tail is 0.10, degrees of freedom 9, and we can go look it up. Let's go to the t-table. So area in the right tail, 0.10, degrees of freedom 9. And you just go down here, you go to the right here. And that's the number, 1.383. That's this number here. So remember how I said 3 is the cutoff, more than 3 steps apart or as far apart, less than 3 steps is close together. Now it's more than 1.383 steps apart is far apart. Less than 1.383 steps apart is close together. So the number 3, again, I told you we're going to use that number 3 as a cutoff for just those couple of slides, then we'll have a better way. This is the number you look up in the table is the cutoff. So every problem has its own cutoff. All right. Any questions on the rejection region part? All right, sounds good. So then the next part is the test statistic part. Look, the test statistic formula is x bar minus mu over s over square root of n. Mu is the king's claim of mu, so we can get that from H1. But all the rest of these things we need to know, and they all come from our sample. In the first example, they were all given to you. But in this problem, the data is given to you, which always sucks because that means there's more work to do. We have to calculate these things. Well, n is 10 because there's 10 numbers. We got to find the average of these 10 numbers, and we got to find the standard deviation of these 10 numbers. Okay, so the test statistic part is where you deal with the sample. So let me go ahead and write these down. Let's start with n. N is 10. Then I want to know x bar. The way you find x bar, what the average of these numbers. So you add them all up and you divide by 10 because there's 10 of them. 206 plus 217 and 209 all over 10. All right, I'm going to go ahead and type this in the calculator. Give me a second here. You should be doing it as well. All right, so what I'm getting is 208.4 for that. Okay, so we found the average of those numbers. Now I got to find the standard deviation of these numbers. This is going to take a few steps, so I'll put it here, but I'm going to erase it afterwards. So to find the standard deviation, you have to first find two sums. You got to find sum of x squared. That means you square each number and then add them all up. Okay, so let me do that. Give me a second here. Okay, I'm getting 435,098 for that. Okay, so square each number, then add them. That's what that means. Then you find sum of x, which means just add the numbers, 206 plus 217, 209. Okay, this is 2,084 because we added the numbers already when we added them here. After we divided by 10, it was this, but before we divided by 10, we had that. Okay, so you find those two sums, then you plug into the standard deviation formula, which is sum of x squared minus fraction line, parentheses, square here, sum of x here, and minus 1 here, square root. Okay. Sum of x squared is this number. So 435,098 minus fraction line, parentheses, square out here. Inside the parentheses, you have to put sum of x. You have to put this number, 2,084. And then sample size is 10. So you put a 10 here and a 10 minus 1 down here. You calculate that, then you take the square root. All right, so let me go ahead and do that. 435,098 minus parentheses 2084 squared divided by 10. Okay, the answer to just this part, I'm saying this so it's recorded in the video so that when you're doing it again later, You can double check. The answer to just that is 792.4. Then you divide by 9. Don't type 10 minus 1, type 9, divide by 9. Now the answer is 88.044444. Then you take the square root of the second root, second answer, and the answer I'm getting is 9.383200117. I don't think it's a good idea to round this number, so I'll go ahead and write down this whole thing here. Okay, so again, the last example we did, example 1, these numbers were given to you. Okay, and again, if they don't give it to you, if they give you data, then you got to calculate them. How do you know which numbers to calculate? Well, it's the numbers you need to plug into the test statistic formula, which I erased, but I'll write it down again. Okay, any questions on this much? I'm going to have to erase this. So before I do that, any questions? Okay, sounds good. So then I'm going to go ahead and calculate the test statistic. So again, we need those 3 numbers first, and then we can plug it into the test statistic formula. So the test statistic formula is X bar minus mu over S over square root of n. Okay, X bar is this number. It's the average of the numbers in the data. And again, mu in this formula is the king's claim of mu. What is the king claiming it is? The king claimed it was 198. And again, if you forgot, you just go back to here, and there it is. Okay, the king is saying it's 198. All right, and then S is 9.383200117. Over square root of, and n is 10. Okay, so you calculate that. And again, this test statistic is just telling me how far apart are these top 2 numbers? How many steps apart are they? And again, when you type it in, okay, look. So I'm going to type in the top first and get the answer. So 208.4 minus 198. The answer to that is 10.4. Then I'm going to push divide. And then when you're dividing by a fraction, you open some parentheses. So I'm going to, on my calculator, the open parentheses button is right above the number 8. I'm opening a bunch of parentheses. On my calculator, I open like 5 of them. Then you type 9.383200117, divide by square root of 10. Answer. And the answer I'm getting is 3.504,954,307. If you round this number a little bit right now, it's not the end of the world, but starting next class, it will be a big problem. So I just prefer not to round it at all. There's my test statistic number. Now, when you're calculating this test statistic on, like, let's say you're not doing it right now, but you do it later on when you're studying, okay? If you get a number like this, but the decimal's in the wrong place, like the decimal's over here or over here, you typed it in wrong, okay? You typed it in wrong. It's got to be this number, 3.5, whatever. It happens a lot of times when the sample size is 10 that you might get the decimal in the wrong spot. If you've got the decimal in the wrong spot, you typed it in wrong. Again, the way you type it in right is get the answer to this, then open some parentheses before you type this in. Then you won't have any of those problems. As long as you're able to get that number, then you're typing into the calculator correctly. And there's the test statistic part of the problem. Any questions on that much? And now I'm going to use this number to decide who to believe. Should I believe the king or should I believe the peasant? It all depends on where this number lands in my rejection region picture. So I'm going to take it back to the rejection region picture. If it lands in the rejection region, we're siding with the peasant. If it doesn't land in the rejection region, we're siding with the king. Let's see what the chat is saying. Reject 80. Okay, let me see. I don't know. 3.5, whatever, right? So let's go back to here. Yeah, 3.5, whatever, is bigger than 1.383. So we land in the rejection region. We land in the shaded region. That's when you reject 80. Yeah, so if you land in the rejection region, then the conclusion, which is the 4th step, is reject 80. If you would have not landed in the rejection region, you would have said, do not reject H0. But since we landed in the rejection region, conclusion is reject H0. I got to write it in words still, but other than that, any questions so far? Okay. And again, when you write it in words, if you're rejecting H0, what does that mean? That means you're believing. So we're not believing this. We're rejecting H0. We're believing H1. But don't write believe. Don't write accept. What you're basically going to write is evidence suggests that H1 is true. But I don't even want you to write H1 is true. You got to be very careful on the wording. Okay. It's not my thing. It's just the way it is. You have to be careful on the wording. You want to basically write evidence suggests, and then you want to write this down. You want to write what the peasant is claiming. Evidence suggests that. Now, I'm going to show you a couple of ways of doing it. The first way of doing it, evidence suggests, and instead of writing this down, you're going to write, instead of writing mu, you're going to write this for mu. Evidence suggests the average number of words per minute Michael reads for all passages read after the course is greater than 198 words per minute. So basically write this thing down that's in a box, but instead of writing the symbol mu, you write mu out in words, okay? That way, I'm showing you how to do it, will always work, okay? But sometimes that way is long, like this one here would be a lot to write. You can write it if you want. So I'm gonna show you another way that works sometimes. If the problem asks you a question, you could just answer the question. The question is right here, was the class effective? Okay. Well, the king is saying no, right? The king is saying the average is the same as it was before you took the course, like the course didn't do anything. The peasant is saying no, the average got higher. The course did do something. So since we're believing the peasant, evidence suggests, you always started with evidence suggests, if you're believing the peasant, evidence suggests the class was effective. That's all you have to write. Okay, so there's a couple of ways. Either write evidence suggests and write down this entire statement for that the peasant is saying, but instead of mu, write it in words, or just answer the question. All right, so that's what I'm going to do for this one. I'm just going to write evidence suggests that the class was effective. All right, that's example 2. Questions? Okay, let me just recap. So I'm going to go over it one more time, but this time I'm going to go over it by just talking about king and peasant. So, okay, there's a big bag of numbers. The king is saying the average of all the numbers in the bag is 198. The peasant is saying the average of all the numbers in the bag is bigger than 198. We're trying to decide who to believe, so we take a sample, calculate X bar. This is like 10 numbers out of that bag, and we calculated X bar, and we got 208.4. Is 208.4 bigger than 198? The answer is yes. Does that mean we believe the peasant? No, we don't know, because I want to know, is it close to 198? What was the average X bar? I forgot already. It was 208.4. I want to know, is that close to 198? Because if it's bigger than 198, but it's close, we're still siding with the king. But if it's bigger than 198 and it's far from 198, then we're going to go with the peasant. So that's the whole question. How close is 208.4 from 198? And that's what the test statistic formula does for you. This is going to tell me how close is the 208.4 and the 198. And the answer is they're about 3.5 steps apart. Now the question is that close or far? Earlier when I said the rule of thumb was 3, more than 3 steps is far, less than 3 steps is close, we would have said far apart, but now we don't use that rule. We use the rejection region picture. I want to know if 3.5 steps apart is close or far. The rejection region picture says if the numbers are more on this side, more than 1.383 steps apart, they're far apart. And the number was 3.5. Let me just write 3.5. Okay, it was 3.5049, some other stuff. But it was definitely more than 1.383 steps apart, so they're far apart. So our X bar was bigger than 198 and far from 198, and that's why we believe the peasant, and that means we believe the class was effective. So that's how that goes. All right, last chance. Any questions on example 2? Okay. Let's see what this says. In 2002, the mean age of an inmate on death row was 40.7 years old. Sociologists wondered whether the mean age of death row inmates has changed since then. She randomly selects 32 death row inmates and finds that their mean age is 38.9 with a standard deviation of 9.6. At the 0.05 significance level, test the claim that the mean age of death row inmates has changed since 2002. All right. So absolute very first thing is we should just try to recognize, is it a hypothesis test problem at all? And I know it is because they say significance level. That's a big one because, again, you only hear the phrase significance level in hypothesis test problems. It says test the claim. That's another big one. Again, anytime they use the word test, you should be thinking hypothesis test. They give you an alpha, a small alpha. Alpha is always going to be a small number, by the way. If they give you an alpha, that's a hint that it's a hypothesis test. But there's different hints depending on the kind of problem. They could just say perform a hypothesis test or whatever. But anyway, this is, I think, pretty clear that it's a hypothesis test. So whenever you perform a hypothesis test, you're going to do it in 4 steps. Okay, so the first step is to write down the hypothesis. You got to write down what H0 and H1 are, what the king and peasant are fighting over. So you got to write down the king's claim and the peasant's claim. First thing is we got to figure out what letter are they fighting over. Again, if there's a sentence in the problem that talks about the sample, which there is here, it says she randomly selects 32 death row inmates, and she's going to ask them, how old they are, right? And finds that their mean age is this and the standard deviation is that. That sentence involves the sample. I advise you to not look at that sentence at all until after you figured out what the king and peasant's claim are. Because again, if you look at this part, you'll think it's a mean problem. It'll turn out you're right. If you look at this part, you might think it's a standard deviation problem. It'll turn out you're wrong. So my advice to you is don't even look at the sample sentence until after you've decided what the argument is that the king and peasant are having. Then when you read the rest, this problem is worded better than example 1 because the word mean is everywhere. Look, in 2002, the mean age was this. Sociologists wondered whether the mean age has changed. On the bottom, test the claim that the mean age. They say the word mean all over the place. If you're looking for keywords, it's all over the place. It's definitely an average problem. As I said, some problems are worded nicer than others. Okay, so it's an average problem. Then the king's claim will always have an equal sign. So put an equal sign there. Now, again, there are 2 populations in this problem that are mentioned, but there's only one that the question's about. One population, so let me tell you what the 2 populations are that are mentioned. First population, let's look here. In 2002, death row inmates, whatever. The first population is all death row inmates in 2002. And the average of their ages, let me go ahead and put in a 2002 here, is 40.7 years old, and no one is arguing about this average. This is the average of all of the ages of all death row inmates back in 2002. But then it says a sociologist wondered something. Well, if the sociologist is wondering something, we have to set up our test to answer the sociologist has a question, we want to answer the person's question. Sociologists wonder whether the mean age has changed since then. Okay, so the other population, there's actually 2 different answers you can give for the other population. One, you could say all death row inmates since 2002. That's probably slightly more correct than what I'm going to write. I'm going to write all death row inmates now. So there's the death row inmates in 2002, and there's the death row inmates now. This is the one the question's about. Okay, and the average age of the ones now, we don't know. They're arguing over it. Okay, so please understand that the whole problem is about this group here. So why is this group even talked about? Just so they can basically hand you this number to use in your tests. The king is going to basically say the average age now is the same as it was back then, and the peasant's going to say no, it's something else kind of thing. Okay, so it's really the only reason they mention this other group is to explain to you where this number came from, and you can use this number in your test. So we're going to put 40.7 here. But again, I don't want you to think of this as saying the average age of all death row inmates in 2002 is 40.7. I agree. The average age of all death row inmates in 2002 was 40.7, but that's not what this says. This says the average age of all death row inmates now is 40.7, and the peasant is going to say, no, I disagree with you. See, the peasant wouldn't disagree if they're talking about 2002 because nobody's disagreeing about 2002. All right, so that's the king's claim. And then the peasant's claim, you're going to put a mu again. You're going to put the same number here, 40.7. We have to decide what symbol goes there. Is it a less than, a greater than, or a not equal to? What do you guys think? No, nothing. Okay. Well, oops, sorry. So it says right here, a couple times, right? It says it right here. So I was wondering whether the mean age has changed. And here it says, test the claim the mean age has changed. What do you guys think? Has it changed? So which symbol do you think it'll be? Okay. So it's going to be not 40.7. Okay. Has it changed? They're asking, the sociologist wondered if the mean age has changed, but it doesn't say the sociologist thinks it's gone up or thinks it's gone down, just it's changed. It's different than what it was before. Okay. So 2 bits of advice. If the peasant doesn't pick a side, then you're going to put not equal to. Okay, if it doesn't say, if there's nothing in the problem that says I think it went up or I think it went down, then just not equal to. Okay. And one other bit of advice, it didn't happen in this problem, but sometimes it happens. If the problem says test equals, if it would have said test the claim that the mean age of all death row inmates is 40.7, like equals. If they ever say test equals, you always test an equals against a not equal to. Okay, that didn't happen in this problem, but I'm just letting you know, they word problems all sorts of ways. Test something is equal to something or test something is something, always against not equal to. Okay, anyway, that's a not equal to there. All right, then, whatever symbol you use in your test, you got to write down what the symbol stands for in words. Okay, so mu. In words, it's the average age of all death row inmates now. Okay. When you write this mu in words, you obviously want to write the word average. You want to get the word all in there. This word now is super important. Okay, make sure you put that, because if you don't, I'm not going to know which population you think the problem is about. Is it about the ones in 2002 or is it the ones now? So that one little word is very important. Or if you wrote since 2002, that's fine as well. The reason I don't write since 2002 is because when they gathered data, they found the ages of death row inmates now. So it's just people now. But whatever, it doesn't matter, either one. You can write now or you can write since 2002, either one. But don't write in 2002, that'd be wrong. Okay, questions on the hypothesis part. Okay, next part, rejection region. Okay, for the rejection region, you got to write down what alpha is, which in this problem is 0.05. And the degrees of freedom, which is n minus 1. In this problem, it said they selected 32 death row inmates, so that's the sample size. So degrees of freedom is 32 minus 1, which is 31. And then you draw a picture. We're going to be drawing the t-distribution today because the king and peasant are fighting over an average. Whenever they fight over an average, it's t-distribution. 0 here. Label it t-distribution. All right, what side is the rejection region on? The left side, the right side, or both sides? Which one?
Both sides.
It's both sides. If H1 is a not equal to, then, so you always look at the H1 to decide what side the rejection region is on. Sum both sides. So you put a tick mark on the left and another one on the right, and you go up to the curve for both of them and shade the ends. Shade the left of the left one, the right of the right one. Okay, so we got that. Now, alpha stands for the total area of the rejection region. Because there's two pieces, each one has an area of 0.05 over 2. You divide it by 2. Only divide it by 2 when it's a two-tail test. Each area is 0.025, so the total is 0.05. And now I'm going to look up, I have to look up two numbers in the table. The one on the right is going to be easier because I know the area in the right tail, and that's what you need when you're looking up something in the t-table. So to find this number, the area in the right tail is 0.025 degrees of freedom 31. Let's go to the table. So area in right tail, 0.025 degrees of freedom 31 all the way on the bottom here. We're going to go like this to the right, and we're going to go down here. And we get 2.040 for that one. So this number here, 2.040. Okay, and then to look up the left one, well, when you're doing a two-tail test, it's pretty easy. You just looked up the right tail. Now to get the left tail, it's just you flip it over the number 0, flip it across. The answer is going to be negative 2.040. Because it's negative because it's on the left side of the table. It's just like the mirror image of the other one, so negative 2.040. And that's the rejection region part. Any questions? Okay. Next part is the test statistic part. So the test statistic formula is x bar minus mu over s over square root of n. So you got to write down what n is, what s is, and what x bar is. Mu we'll get from the King's claim. So you write down those things and then you plug it into the formula. N is 32. So we're looking at this sentence now. They selected 32 inmates. Their mean age is 38.9. That's x bar. And the standard deviation of those ages is 9.6. In some problems, they give you data and you have to calculate those. But anyway, to this problem, they've calculated it for you. So you just plug in to this test statistic formula. All right, so x bar is 38.9. Mu is the King's claim of mu. Let's go back to the King's claim. Here it is. He's saying mu is 40.7. So you can put 40.7 there. S is 9.6 over square root of 32. You calculate this on the calculator. 38.9 minus 40.7, get the answer. I'm getting negative 1.8. Then divide. Again, when you divide, open some parentheses before you type this fraction in. So open parentheses, 9.6 divided by square root of 32. I'm getting negative 1.060660172. All right, so if you got that answer, you typed it in right. Any questions on the test statistic part? Conclusion here. So our fourth step then is the conclusion, but again, I have to decide, should we reject H0 or not? So what we're going to do is we have to look to see where does this number land in our rejection region picture. So we're going to go take this number back to the rejection region picture. The number was, what was it? Negative 1.06066. I erased the rest, but whatever. It's negative, but it's not past negative 2 point whatever. It's not past the cutoff line. So it's over here somewhere. Okay, it's not over here. It would have to be negative 2 point and whatever, something bigger than negative 2 point whatever. We're landing in the region that's not shaded. So we're not landing in the rejection region. Okay. So that's the deal. You have to figure out where this number lands on the number line, and it does not land in the rejection region. If it lands in the rejection region, you say reject H0. If it does not land in the rejection region, your conclusion is do not reject H0. The first part is either, again, reject H0 or do not reject H0. This time it's do not reject H0. Okay, Then we got to write the answer in words. When you write this first part, it's always about H0, but then when you write the answer in words, it's always about H1. Let's go back. Do not reject H0 means we're sticking with H0. We're not believing H1, but you got to talk about H1. Not enough evidence. So if you want to believe H1, you're going to say evidence suggests H1 is true. Don't write H1 is true. Just write evidence suggests H1. But in this case, we're not believing that. So you're going to say not enough evidence to say this. Not enough evidence to say that. But when you write this, write it in words. Instead of writing the symbol mu, write that symbol down. Okay. So let me start off by writing not enough evidence to say. And now I'm just going to write down what H1 is saying. Mu is the average age of all death row inmates now. Okay. That the average age of all death row inmates now. So I just wrote this, is not 40.7 years old. Is not 40.7 years old. That if you read the sentence, you'll see a double negative here. It says not enough evidence to say that the average age of all death row inmates is not 40.7 years old. And I know in English classes, English professors tell you when you have a double negative, you should rewrite it, like kind of cancel out those negatives. And what I'll tell you is that in a stats class, I would advise you not to do that because nothing is 100% in a stats class. You don't want your sentence to sound like you're saying something is for sure this, because nothing is for sure, okay? So I'd rather you leave the double negative in there. If you do cancel out, it might be okay, but depending on the way you word it, it might sound like you're saying for sure it's 40.7 or something like that, you know, and you don't want it to sound like that. So don't be afraid of double negatives in a stats class, I guess is what I'm trying to say. All right, we're done with example 3. If you guys get it, any questions on example 3? Let's move on. We got to talk about type 1 and type 2 errors and the meaning of the significance level. So let's go ahead and do that. So the thing is, when you run a test, when you run a hypothesis test, you get a conclusion, right? Like believe the king or don't believe the king, right? Reject H0, do not reject H0. And the king, he's on trial, so to speak. He's either telling the truth or he's lying, but you don't know what situation, like you don't know if he's telling the truth or lying. So there's basically in every hypothesis problem, there's really 4 situations you can be in. And we have this little table over here. The king is, H0 is true, meaning the king's claim is correct, he's telling the truth, or the king's claim is false, the king is lying. You just never know if the king is right or not. You never know. So whenever you run a test, or like anytime a person's on trial, you never know for sure if the person is innocent or guilty. You never know, okay? And then, so this is like, think of the top as like the truth, you know? The truth is that, you know, so either the king is telling the truth or he's lying. You just never know which of those situations you're in. And every time you run a test, your conclusion is going to be reject H0 or do not reject H0. So these are like the conclusions of your test. So that gives us 4 situations. Let's take a look at this one first. Let's say you're in that situation. Then the king was wrong, he's lying, and you said don't believe the king. Then you made a correct conclusion because he was lying, you said don't believe him. So correct conclusion, all is right with the world. Again, you never know which of these 4 situations you're in. But if you happen to be in that situation, everything's great. It's like saying the king is guilty and you said send him to jail. Great. You send a guilty person to jail. Fantastic. That's what's supposed to happen. If you're in this situation, again, you never know which situation you're in, but if you were in this situation, the king is telling the truth, and you said don't reject his claim, don't stop believing him. Like believe him is what you're saying. He's telling the truth, believe him. If that's the conclusion you came up with the correct conclusion again. All is right with the world. The king was innocent, you said don't send him to jail. Great. Let's take a look at the other two situations. If you're in this situation, again, you never know what situation you're in. But if you're in that situation, the king is telling the truth and you said don't believe him. You've come up with an incorrect conclusion. I'm not saying you did the problem wrong or you're going to lose points, but whenever you perform a hypothesis test, you don't know for sure that your conclusion is the right one. You just tell me what conclusion you ended up with. Your conclusion depends on your sample that you drew, okay? But doesn't mean that whatever conclusion you came up with is right, okay? If you're in this situation, you came up with an incorrect conclusion. The king was telling the truth. You said, don't believe him. It's like saying the king is innocent, but you sent him to jail. That's an error. We call that a type 1 error, okay? And the probability of making this kind of error is alpha. Be prepared on the quiz next time and future quizzes for me to say what's a type 1 error. All you have to say if I ask you what is a type 1 error, all you have to say is it's when you reject H0 when H0 is true. So memorize that one. A type 1 error is when you reject H0 when H0 is true. So if I say what is a type 1 error, all you have to write is it's when you reject H0 when H0 is true. That's all you have to write. Okay, let's take a look at this situation. Again, you never know what situation you're in, but if you're in this situation, the king was lying and you said, don't reject the king's claim. So king is lying, you said, believe him. You've made an incorrect conclusion. It's kind of like saying the king is guilty and you said, don't send him to jail. You've made an incorrect conclusion there. That's called a type 2 error. And the probability of making this error is beta. Unfortunately, we're not going to have time to talk about beta, so that sucks. So don't worry so much about it. But be able on a quiz or an exam for me to say, be able to answer the question if I say, what's a type 2 error? So if I say, what's a type 2 error? All you're going to say is, when you do not reject H0, when H0 is false. If it's starting to get confusing, this is what I would do if I were you. Memorize type 1 error. It's more important anyway. Type 1 error is when you reject H0 when H0 is true. And then if I ask you what's a type 2 error, just say the opposite. Instead of saying reject H0, say do not reject H0. And then instead of saying when H0 is true, say when H0 is false. So type 1 error is when you reject H0 when H0 is true. Type 2 error is when you do not reject H0 when H0 is false. So be able to say those two things. And then the last thing is the meaning of the significance level. So the significance level, which is the area of the rejection region, which we call alpha. It's a probability of making a type 1 error. So you know how this works. Every time we have a probability, we have to explain what it means. How do you explain the meaning of a probability? You got to say something like, if you do something many times, okay? What do we have to do many times? We have to do the hypothesis test over and over again many times. I'm not saying do the same exact test. You do the same test, but you have to take a new sample each time. Every time you run a test, you have to first collect the sample, right? And then calculate XBar and then run the test and see who to believe, okay? So if you do that over and over again, take a sample, run a test, get a conclusion. Take another sample, run the same test again with the new sample and get a conclusion. Then take another sample, run the test, get a conclusion. If you do that over and over again, you're gonna make a type 1 error, whatever this alpha percent is of the time. So what's the meaning of the significance level? Okay, this is how I'm going to want you to write it. If I say, let's say the significance level in a problem is 0.03, okay? And I say, explain, what's the meaning? The problem will say something like, explain the meaning of the significance level when you run a hypothesis test at the 0.03 significance level, or something like that. You're going to say this. If you perform the same hypothesis test many times, so you got to say run the same many times. You got to do the same test many times, but each time with the new sample. And again, let me put the alpha equals 0.03 here. If you perform the same hypothesis many times, each time with the new sample, you have to write down, you'll make a type 1 error, but I don't want you to write type 1 error. I want you to write what a type 1 error is. So you're going to write, you will reject H0 when H0 is true. Again, that's a type 1 error. You'll reject H0 when H0 is true about, and then you got to just change this number to a percent, about 3% of the time. Okay. You reject H0 when H0 is true about 3% of the time. On the quiz, I have no idea. Is it going to be a left tail, a right tail, or a two tail? Just it's going to be random. So you have to know how to do them all. And then make sure you're comfortable on how to do all left tail, right tail, and two tail hypothesis tests for mu, because that's all we've done so far. Be able to explain what a type 1 error is. Remember, type 1 error is when you reject H0 when H0 is true. Be able to explain what a type 2 error is. It's when you do not reject H0 when H0 is false. And be able to explain the meaning of the significance level. And again, the way you're going to say that is, if you run the same hypothesis test many times, each time with a new sample, you reject H0 when H0 is true, that's type 1 error, about, and then just change this to a percent, about that percent of the time. Meaning you will send an innocent person to jail about 3% of the time. So about 3% of the time, you'll say the person's lying when he was telling the truth. Okay, guys, if you get all that, that is the end of the story for today. We're done for today's study. Super hard, guys.